Is it fair to say that Mina is also a decentralized distributed computer?
I call it that all the time. Yeah, welcome. I'm basically, today I'm going to give a talk about how Mina works. So I'm going to start from the ground up. I'm going to talk about, what a blockchain is, what it looks like to apply zero knowledge proofs to a blockchain. And then talk about the properties you get at that, talk about a consensus sum, and then finally at the very end, I'll wrap it all up by talking about zkApps in depth. So it's meant to be very interactive. Please ask questions as we go. Like I said, I might miss things, so just stop me, raise your hand, I'll call on you. I'm going to do a very short little presentation on where Mina sits in the world of systems. Like, why is Mina unique? And I think this is a pretty good way to think about why Mina is so unique. It also helps explain some of the unique challenges you have to deal with at a very high level as like a developer for Mina zkApps. So if you think about systems, you can kind of divide systems up into these categories where one axis is replicated versus distributed. Another axis is permission versus permissionless. So if you take some examples, like looking at each of these grids, what's an example of like a permissioned replicated system? Well, in the database world, a really simple example is like MySQL. The way that MySQL works, if you have a cluster of MySQL servers is, well, if I only have one MySQL server, it's not really a distributed system at all in terms of like how you're structuring. You just have one server, but to scale it, we need to have many servers. And the way you usually do that is you're just like copying the data onto every single server so that every single server can serve a query. And then you're round robining which server you're sort of asking for information in MySQL. And so in that sense, like MySQL is a replicated permission system. It's permissioned, it's not like people are going to come in and run their own database on top of yours. They're not going to join your network. You're running all the SQL servers and you're replicating all the data through it, through a very antiquated terminology of master-slave replication. That's what they call it, where there's one server that receives all the writes, and then it tells all the other servers about what was written there, and then they replicate the data locally. Another example, requires a little bit of, thinking. It's not very obvious, but I would also say in this category is like a web page, right? Web pages, you can permission them. You can permission them behind access. You have to authenticate and you control that. Maybe it is permissionless, but typically it is permission. And it's also replicated. Every single time you go to a web page, you're downloading JavaScript code and executing that JavaScript code locally to reproduce the web page in the environment, right? And so it's replicated across a whole bunch of computers and it's permissioned. And we move down to the distributed and permissioned model. We have things like Bigtable, or if you've heard of Cassandra. These are other types of databases. It's like literally on its last leg. And so these kind of databases, they work differently from MySQL in the sense that they're not replicating all the data around to all the different servers. They're distributing the data between all the different servers. Every server has different pieces of the data. And when you send a query to the network first figures out which servers do you have to talk to get this data, and then goes and talks to all those servers to get the data and collects it back. So if MySQL had 10 terabytes of data, every single server running in the MySQL cluster has to have 10 terabytes of hard drive storage. In Bigtable or Cassandra, these databases, you actually have every single server just has to have maybe 100 gigabytes or a couple hundred gigabytes of storage, and that 10 terabytes of data is split across all those systems, so it's distributed. Another example of distributed permission system would actually be a web server. So like a web server, by comparison to a web page, when you go and you hit a web server, you're hitting the load balancer, and the load balancer is going to send you to one of the servers that's going to actually run the computation once to give you the response. Not every single web server is actually repeating the computation, so it's not replicating that computation. It's just distributing the computation to different servers in the network. If we go over to permissionless and replicated systems, well, this is basically Ethereum and every other world computer blockchain that's EVM based or anything like that. Because it's permissionless, anybody can come and join and participate in the network, right? It's open, anybody can run an Ethereum node. But it's replicated because every time you are running an execution inside the EVM, every single computer on the network is executing, right? You're literally replicating the computation because that replication of computation is how you erode trust. The fact that you redo the computation means I don't trust anybody else who did the computation. If we come down to this grid here, permissionless and distributed, this is where Mina lives. And to my knowledge, nobody has been able to point out one that fits here except for Mina so far. Mina is the only system that is both distributed and permissionless. Anybody can come and they can join Mina. We do replicate proofs initially, but we throw out those proofs very quickly. All we're doing is replicating the verification of those proofs for a short period of time before they get merged back together. All the computation that happens on Mina is happening off-chain in a distributed fashion. Only one computer needs to do that, and then it's just submitting the verifiable proof of that computation to the Mina network. And so it's really the only thing that fits here in this category of distributed permissions. There are some things that kind of move towards this direction a little bit, but nothing that goes fully into this category. And in general, it's kind of interesting because normally when you think about this axis right here, what you're getting with this axis is basically scaling. But traditional systems, like an Ethereum that are doing scaling through L2s and stuff, are also pushing along this axis. In order to scale Ethereum at L2, you have to centralize and become more permissioned over time. Even sharding in Ethereum is basically splitting things up into smaller and smaller buckets of permissioned centralized systems. And so Mina is the only one that's really moving along this direction of the axis. Without sacrificing permission nature or decentralization, we still maintain all the decentralization and permissionless behavior. And we have complete distribution of not only the computation, but also the data. Because you can use private inputs to your snark to basically not have to share the data with the network, you have no reason to replicate data on the network. You can actually keep data completely off the network in a distributed fashion. And this is where a lot of the unique use cases for Mina come. It's all from the concept that you can have distributed data and distributed computation. That's what makes Mina unique. Any questions on that?
Where is Celestia?
Where is Celestia? It's replicated. All the data is replicated in Celestia. So it's permissionless replicated. I would say IPFS is also permissionless replicated. They have some degree of distribution, but they require replication. Yeah, throw out anything else. Anybody have other ones?
Any MPC networks?
Huh?
Any MPC networks?
Yeah, I mean, a lot of multi-party computation networks are being done on top of permissionless replicated systems. So they're replicating the verification and the bits of information that are being spread along. I don't know a lot of MPC networks that are truly like peer-to-peer. They always require some sort of layer for global state synchronization, and that's where Ethereum comes in. Mina is a global state synchronization layer that, is in that category. So yeah, NPC by itself offline you could completely do, but the need for some kind of global layer to aggregate information back to and synchronize is what kind of pushes to these systems. I recently learned about one that's kind of straddling this boundary a little bit. What was the name of it? I can find it really quick. No, Aleo is replicated. Aleo does not merge everything back into a recursive proof. So they do distribute some offline computation, but they have to constantly replicate all the verification of that forever. They don't merge things back in together the proofs. They have to always replicate every single proof that was ever submitted to the chain and serve it forever. And if you want to join the chain and check the chain state, you have to go through and verify every single O of N proofs. So they are distributing the computation in some sense. So they're kind of on this border, but they're replicating all the verification and the data required to sequence it together. There was recently somebody shared with me what I was looking at. Oh yeah, Oasis is a little bit on this boundary, where Oasis is actually a permissionless replicated system in the sense that they're in this category because they're running EVM, but the EVM has like a bunch of precompiles for some set of, cryptographic primitives that allow for privacy. So they sort of have some distribution aspect, but if you actually dive into how their EVM works, all the computation has to be replicated. It's just hidden behind some cryptography that hides the information. So they're kind of like, I would say they're here, like getting close to it. Aleo, I would say, is like maybe here, just barely dipping their feet into the other side.
Why do you think there hasn't been many distributed permissionless blockchains like Mina? This design actually isn't scalable.
So I think there's a few reasons. One, it's really hard to build. I mean, you can see how many years it took us to build. Another thing is that people are really bought into the existing ecosystem. Everybody wants an EVM chain, and an EVM chain is inherently not going to work in that model. And you could try and retrofit it, which is what they're doing. But I always say it's kind of like changing the engine on a moving car. I think the other thing is that to a certain extent, Mina is the first one that's really proved this, and it really hasn't, proved it fully. Like, I believe it. People who are here might believe it, but Mina today, is really slow, right? That is on purpose. That's because we've entirely prioritized building the system out and worrying about scalability later. But the whole design of Mina, as I was going over, is designed from scalability from the ground up. It's just an engineering task that hasn't been done to scale it, pretty much. You know what I mean? And so in that sense, people look at Mina and they see the current properties of it and don't fully understand the design and don't see this as necessarily being scalable. I hear that a lot. Like, people are like, oh, the TPS is so low. Oh, you have this account model. Yeah, exactly. Block time. How can you ever scale it? And the answer is we just purposefully haven't. It's been a very explicit resource decision to not scale Mina yet, because all the design there is there to scale it. Like, we're sort of not worried about it. None of the engineers are really that worried about scaling it. We don't see that as a problem in a sense. But in that sense, because we haven't done it yet, it's not really proven to the world.
What were the significant gaps between Mina and them that are interesting to know about, to understand?
Probably the easiest one to compare directly is Alio. Alio is also a blockchain, which is based on zero-knowledge proofs and has a programmability layer for zero-knowledge proofs. Alio as a blockchain is like this completely private L1. So instead of doing the public L1, they're basically doing a fully private L1 that comes with a lot of problems with consensus perspective. But the way they get around that is just by doing proof of work. The big difference between how Alio and Mina works, at the end of the day, the important one to understand for the differentiation in this category, is that Alio receives proofs and transactions and puts them into a block, and that's it. It's done. Everybody who wants to join the chain has to go through and verify every single proof that was ever submitted by any application. If I want to verify an application state, I can't just look up the statement for the application state. I actually need to download every single block that ever had a transaction with that in there and verify all of those transactions. And if those transactions involve interacting with other applications, I have to do the same for all the other applications too. So it becomes this giant, because they're not doing that part where they're, that layers I was showing before, sort of like the tower and user proofs and the transaction proofs that merge together into blockchain proofs, they can't tell the same story as a whole about the distributed and permissionless system, because you can't you join it as if it's a permissionless replicated system. So you distribute the computation, but you don't get any of the benefits of it.
I see. And how would you compare Mina to BitTorrent in this case? Like, because I imagine end up in the lower right quadrant, but then...
I think BitTorrent that's actually a good point. I think Torrent is down here more. Torrent does replicate things for redundancy. And so it's a little bit in the boundary here. I guess like IPFS is also a little bit there because they replicate things for redundancy, but they don't fully replicate it all the time. You do the proof of storage thing in order to prove that you have the storage that you're supposed to have locally, but you don't store the entire database. It's not quite MySQL, but it's not quite Cassandra, right? And so BitTorrent is kind of here. Like, it's permissionless. Anybody can come and provide data. That data can be checked by the network. It is distributed, but also I guess this is what I would say. The data in BitTorrent is replicated. The packets are distributed in a sense. You know what I mean? Does that make sense?
Yeah.
Because if I'm seeding a file on BitTorrent, I have the whole file, right? If I'm going to be a seeder, I download the entire file, all the time. BitTorrent can never be used for private information.
It's interesting because this comparison and the comparison before with or the strategy to layer the Merkle tree in order to level out the proof work, the load of proofs, seems to come to being able to look at the problem from a different perspective and look at another way to cut it up. Yeah, so I was interested to hear how you distinguish BitTorrent so it's a packets.
It's like it's straddling it because like network activity is distributed, but data is replicated. It's distributed network activity to replicate data.
Right. So from micro level, from a user level, from a user perspective is one thing, but then from a network perspective, it's another.
Right. Yeah.
Yeah. Okay. Thanks.
So in terms of computation, I guess it's certain that Mina achieves everything that Ethereum can achieve in theory. But in terms of storage, can Mina scale enough to actually be considered a storage layer? I mean, like, for instance, IPFS, can Mina even, be used as IPFS is used? Because in that we need live data.
It never would be, I don't think. We can increase the storage and like have a system for bonding for storage, but we'll never have an IPFS like data storage layer directly in Mina.
So then, like, in that sense, does it make sense to actually compare Cassandra to Mina? Because one is a data layer and the other doesn't.
I'm not really comparing Cassandra to Mina. I apologize if it looks like I am. I'm just trying to categorize where different things fit in systems, but I wouldn't compare Cassandra to Mina at all. Where you can kind of compare it, though, is don't think about Mina as blockchain. Mina is bigger than the blockchain. Mina is a distributed permissionless computer. Anybody who's running a light client and joins the network and is doing computation is participating in that computer. And in that sense, you can build Cassandra on top of Mina. In other words, you can have distributed data that's even private and accessed across different servers that connect to Mina and provide that data. The blockchain itself will never have the storage. Computers can come and join the network with the storage and provide it. In other words, IPFS kind of things can be layered on top of Mina, but not the Mina blockchain itself, not the L1. Right.
Then can you describe like a perfect data storage layer that would fit into Mina? Like how a perfect data layer should look into Mina? I don't know.
I mean, how a perfect one should look, that's hard because perfect is not possible with data storage layers usually. You always have to make some kind of concession. Maybe one day we'll figure it out, but I would say I can get some examples for how data storage layers could work that's unique to Mina. Like one thing I've thrown around a little bit recently is this idea of sort of like a zkSQL. You can have a shared schema that's committed to on Mina, and different computers can come and submit proofs about the data that's being inserted into their local copy of that data. That's their local distributed data set. They're not sharing that data set with other people. And then you, as a user, can basically have the schema can have a permission model around what can be accessed and what needs to be anonymized or aggregated together for certain kinds of queries, like permission layers that you can prove for access. And then you can submit queries to Mina, and Mina runs a distributed join operation that allows these computers to come in and are incentivized to come participate with their data and come provide it. So as an example, you can imagine like Facebook and Google and different companies like this, they have all this user data. This would be an evil way of using it, but it's also a real way. They could come in, instead of like selling their data to data brokers and then data brokers reselling it to third parties, they could keep their data. And they could actually just allow people to come query their data, but not just query their data, query the whole set of user data across all these services. So advertisers could get like anonymized information about users using the zkSQL thing. And all of these big companies are coming and actually attaching their data to the network and then helping assist in the distributed join operation that's facilitated by Mina. So that's like that's an example of the distributed data aspect, right? Different parties have different data. They can provide proofs around that data. People can provide proofs around accessing that data. It can be aggregated, anonymized, however you want to set it up, but it just becomes one schema interface into all the data by different companies.
Is having a virtual machine a factor in dividing replication and distribution?
So yes and no. The answer is like, so you can imagine that you take a zkVM and you plug it into Mina. It's one of the things that's in discussion. I'm like not totally sold on it yet. But it's something people bring up sometimes because we do have O1VM now, which is a framework for building zkVMs. And so you could plug that into Mina and have some form of on-chain execution. It's initially replicated. So it's not even really initially replicated. It's a little tricky. You'd have to design it very carefully. That's the issue with like the zkVM kind of route. You need to replicate until the proof is produced because you have this asynchronous proving thing. You have to replicate the execution of that virtual machine outside of zero-knowledge proof. And then once it's proved by a single person, you never have to replicate it again. So you have like short spans of replication. And in a sense, that's even true on Mina today. Like you replicate the actual transaction application as a block producer initially, but then you very quickly stop replicating it. It's like replicated once across the servers, and then no other server ever has to redo it again because it gets proven. So like there is always sort of some level of back and forth here, but what you're really getting with Mina and the real power of it is the fact that you have a very limited scope of very temporary replication that happens, which is just the gossip network essentially. The gossip network is the very temporary replication layer. But all of the compute that happens off-chain, anything that's happening inside of a zkApp is never replicated on-chain. And that's the thing. So if you put a zkVM here, you would have short-term replication, and then you would have to run that, and then you would be able to throw it out, which still has a lot of benefits. But as long as you're working with the zkApp world off-chain and not using a zkVM, you're getting full distribution, no replication over.
And this is a silly question, but the reason why Ethereum is called decentralized computer was I thought it was because of the virtual machine. But since Mina doesn't have virtual machine, are we allowed to? Is it fair to say that Mina is also a decentralized distributed computer?
I call it that all the time. I think it is because this is the way I think about it. It's like it's a decentralized distributed computer that any device can join. Your phone can join, do a computation, and leave. And that is still participating in a distributed computer. It's still rolled up into the same computer. It's part of the same global computation that the Mina blockchain is doing, right? And so it is a distributed computer in a different way than like Ethereum is. So to start out, we'll just do a really quick intro. I'm sure everybody knows this here, but I think it's useful because sometimes people don't always think about this too much, and it's useful for, you know, anybody who might be watching the video as well, of like, what is a zero knowledge proof? Not like what is the cryptography of it, but just abstractly, what a zero knowledge proof is. And essentially the way you can think about a zero knowledge proof is the way you write it. Well, should I do the witness thing? I won't do that for now. Abstractly, you have some set of constraints that you can write down. And then from that set of constraints, you can derive a proving key and a verification key. Okay, these are two cryptographic values that you basically derive directly from the constraints that you write down. And by writing down these constraints, you can essentially prove anything, right? These constraints are just saying, hey, given some input values, here's a whole bunch of constraints that have to hold on those input values. And so from that, you get this proving key and this verification key. And the way you can use these is you can basically do a proving operation where you're taking in the proving key, you're taking in some private input, and you're taking in some public input. And then from that, you can get out a proof. And this is just a few kilobytes of information. It's some cryptographic data. And then what you can do is you can take the verification key and the public input and the proving key, and then you can verify that proof. Okay, this is a cheap operation that you can do once you have the proof. You don't need any of the private inputs to do this. You don't need the proving key, which is this big blob of data. You only have to know the verification key and understand the constraints they were derived from, and then you can do this operation to verify it, and it can be done in tens of milliseconds. What a recursive zero-knowledge proof is basically when you do this same system, but you're also taking the proof and treating it as an input. Actually, let's do it this way because it's usually how you do it. This is what you want to do. You're basically taking the proof and you're putting it in as a private input to the next proof. Okay, that's the recursive part of recursive zero-knowledge proofs. And so if you think about this now, the constraints that you write down that are reasoning about these inputs are just doing this whole process inside of the constraints, right? If you take this whole thing, or rather this part of it, the verify step, and stuff it into the constraints, now you can do this operation where you can keep on feeding proofs back in over and over and over again, and that's how you're building up this recursive zero-knowledge proof. At the end, you're still up to the same small proof, but now you've encapsulated the same constraints run through the program multiple times, right? So you have a static set of constraints, and then you keep on updating the inputs and like recursively proving more and more stuff every generation. Any questions about that before I move on? I think everybody knows this.
You give a bit more context to what the constraints are?
Sure. The constraints can really be anything, right? You can prove anything with constraints, any kind of proof that you write down. But what's interesting about this is like, that's a very abstract concept, right? It's like, well, what do you actually do with constraints? Because you can do anything with it, I think the most important thing to really understand of what you can do with constraint is the concept of verifiable computation. In other words, if I want to compute something, any value that I want to compute, right? I can take that computation and I can turn it into a constraint system which is going to provide constraints essentially on the execution trace of a program, okay? And this is really the abstract way that I like to think about the constraint model. Because when you think about it as verifiable compute, it's like any computer program that you can run, you can encode as constraints. There is this sort of little asterisk here, which is that you can do verifiable compute of finitive things. So in other words, you can't write a for loop that's like, for 0 to n, where n is just any value. It has to be like for 0 to 100 or for 0 to 1000. But because you have this recursive layer, right, you can basically still model any program using the system, because even though each individual set of constraints has to be finitive, you can't like have it be infinite, you can keep on feeding it back in and basically use that to stage the various steps of your program computation. And so the real thing to think about constraints here, what you're really getting, the power of this, is this concept of verifiable compute, that you can compute anything and then you can prove it. Does that answer your question? Okay. Yes?
So they've been saying that proof aggregation and recursive proofs are not exactly the same thing. Does it matter for Mina, or what's the difference basically? I've been wondering.
Proof aggregation versus recursive proofs? Well, proof aggregation is just when you collect a whole bunch of proofs together, right? Is that usually how people are using that term? That's how I've heard it used in different contexts. It's a little vague term, but is that what you mean?
Yeah, but they say they say recursion is not the only way of aggregating proofs. So I've been wondering, is there like other ways of actually adding proofs inside other proofs and maybe improve the process? I don't know.
So I think probably what people are referring to there, I'm not 100% sure, because with the industry in general, people use these very big terms and use it in multiple contexts, is mostly folding. That's the very common scheme besides recursion. Folding is, instead of doing the step, and I'll talk more about folding at the end, instead of having this recursive step where the proof is fed back in to re-verify it, what you're doing is you're actually taking a whole bunch of executions of these public and private inputs, and you're using some cool math trick that I don't fully understand, but I could try and talk about sometime if you're interested, where you basically combine them all together into one set of inputs. So in other words, the constraints have to hold against a whole list of these inputs, right? But you can merge all those inputs together such that the constraints will still hold when you check the proof, okay? And so it's the idea of like either recursively verifying some prior proof, in this case, which is a very powerful primitive, but has some performance trade-offs, versus having to take all the public and private inputs all in one batch and then merge them together. You'll notice one of the big trade-offs with that is that once you make that batch, all the private inputs have to be known for that batch. In other words, you're losing the ability to sort of hand off part of the computation you've done to somebody else and then continue it, right? If I have some private input and somebody else has some private input, we can't aggregate those proofs together without recursion unless we're going to share those inputs with each other.
One last one for the video. So the constraints is your zk circuits as well, isn't it?
Yeah.
Yeah.
I mean, I really don't like the word circuit, and I will use it throughout this talk sometimes because it's become an industry standard. And people, once again, with a lot of terms in the industry will mean different things when they say circuits. But the very first version of circuits was before we were talking about recursive stuff, okay? And so a circuit was just basically, the way you think about it is it's like a directed acyclic graph of your constraints. That's basically what they mean when they say a circuit. It's this idea of taking an execution trace where different values in the execution trace are derived from other values. And so you can sort of build a big graph from it. The reason I hate circuit is because circuit literally, is cyclic by nature, whereas constraints are always acyclic. So that's why I hate the word circuit. Nowadays, some people are trying to use the word circuit only to refer to the concept of when you're using recursion, because they've realized that you need a cyclic nature to actually make it make sense. But even that doesn't make sense because you can only take the output and then feed it back in as an input. You can't actually have the individual nodes of the graph of constraints talk about each other.
Recursive.